All right, well, let's get started. So today we're going to talk a little bit about how manufacturing interfaces with our new dilemma that I guess we've been dealing with for about 18 months, off and on. And primarily what we're going to talk about is first sort of an overview of what exactly is going on with the pandemic in terms of manufacturing. That's somewhat important these days because everybody is now slowly trying to return back, depending upon how the vaccines are working, and they seem, most of them, rather effective, especially for young people. I'm sure you guys don't have much to worry about, but older people like myself in their 50s and 60s and 70s may have a little bit more of a concern because of the degradation of the immune system and so forth. So the last portion of this class is, again, we're going to go through three different main topics I thought were important. One is microscale transmission. By now, we kind of all have a pretty good idea of what's going on in terms of coughs and sneezes and things of that sort. But there are other transmission modes that are questionable. For example, contact with surfaces, whether people can actually contract many of these diseases. But we want to enlarge our thoughts on not just simply COVID-19, but several of the other diseases that are out there. And manufacturing, of course, has many, possibilities, right? It's not always just pieces of metal or wood or plastic, but it could be also food. And that, of course, is central to a lot of what we're dealing with. Almost all of us eat food every day. So if you're going to eat food, you probably are worried about decontamination and propagation and so forth. And the number of outbreaks of things like salmonella and other types of pathogens that propagate is rather large. If they received as much press as COVID-19, you probably wouldn't want to put another piece of food in your mouth ever again, because I can tell you there's quite a number of things that go wrong in terms of how things propagate, but human beings are fairly resistant, or resilient, I should say. But in general, there are many other forms or diseases we need to worry about. So we'll break it up into three parts. Part one will be microscale transmission. So that's more or less, between ourselves, inside a room, what goes on. Then part two will be more on, well, what are you going to do about it in a workplace? How do you decontaminate things? What are the possible mechanisms that you can use? And then finally, something that is now becoming even more important. I mean, each day now, the macroscale propagation and contact tracing. That, of course, now is a big part now of the campus. I think as of April 19th, people can walk around with their cell phones or whatever device they have with different color-coded badges. And of course, the badges are going to indicate, various aspects of the disease, whether you've been tested, whether you have a vaccination. We've crossed the Rubicon of privacy concerns. I think those are now being abrogated, more or less, starting in the fall, all students are going to be forced to be vaccinated or not attend. I believe that is now the ruling that is coming. So in general, for the fall, we should assume that if you're not vaccinated, you're going to have kind of a problem on campus, I would imagine. And I'm not really sure legally exactly what's going on in that regard, but nonetheless, that's on the table now. The faculty and staff have to be. I mean, there's no, they're employees. We're being forced even to get the normal flu influenza shots. So that's something that really can't be, abrogated or wished away. So there are a couple of different things that sort of motivate this. One in particular is food manufacturing. Some of you that work in my group know quite a bit about this, but generally speaking, food manufacturing dwarfs almost all other manufacturing that we have worldwide. I mean, when you start to think about it, the packaging, processing, pieces of material coming out as slurries, then solidified, then freeze dried, then packaged, then transmitted. All of those different things, of course, touch on many of the different aspects we've had even in the first couple of projects. In fact, the last one that you've had on the effective properties of materials, that's a central part of food manufacturing. In fact, how people ascertain what texture is like, what taste is like, those are effective properties, right? I mean, when we put a candy bar in our mouth, that's a combination of many different ingredients that are coming together to stimulate certain things that we like, hopefully. I mean, that's why we like candy bars. But those in general, there's a lot of effective property analysis that goes in there. I work somewhat with the Mars Foundation, so Mars candy bars, Milky Way, all that stuff. They're deeply into the effective properties of candy and things of that sort. So there is an aspect there that touches upon many things we've already learned. So the primary things I think of interest in food is generally the, food system, I guess, security and safety and how you process it. And unlike other types of processing of materials and that sort, there's one main issue, which is biofouling. That's very important, meaning that if you have a 3D printer and you print up a piece of metal, you hope it doesn't clog or that it doesn't produce inconsistent materials. That's more or less a process control issue. But when it starts to come to food, we have an extra added issue that if there's residual food from the previous print or residual pathogens and things of that sort, that's going to lead towards a problem with food manufacturing. So it takes on a whole new life that's far more complex than just simply what we have when we're manufacturing normal materials. Oftentimes, I think what has happened in industry there is this concept, and I'm trying to highlight them in red, the so-called digital twin, which is basically a digital replica of some complex manufacturing process. And that could be, as we see here on the upper left, primarily things like, what we would, crystallize in our own minds that, there's an assembly line, there's something getting slopped onto a surface, there's, after it gets heated, packaged, and so forth, then it gets onto a truck and it's transmitted away. That's an oversimplification of the process as it stands, but generally speaking, that has more or less fairly straightforward implications on how we have to control things. One thing that's a little bit more complicated is what we've looked at before, is how you combine all of these different constituents together to get some type of property that you want. And in this case, property is no longer limited to thermal properties or electrical properties or mechanical properties, but it also has texture and taste and things of that sort, because of course the consumer wants a certain effect from food as well. Then we start to get into the whole idea of robotics, but robotics in this case is going to encompass things like drones, monitoring of fields, monitoring of pesticides, things of that sort for large scale agriculture. That's becoming relatively commonplace these days. And there's a number of people on the faculty in the College of Engineering that work actively in this area of drones and for use of societal needs. And of course, one of them is ag. Then there starts to also be worker safety. And when you start to think about, the types of things workers are exposed to in terms of solvents, things like, for example, meats, things of this sort, where you have all kinds of issues that are, involving, live animal products, things of that sort. They are obviously exposed to things that are a little bit hazardous as well. So we have those kinds of issues. And then finally, more pie in the sky stuff, but becoming much more commonplace, which is, robotic harvesting, things of that sort. And so all of those things, of course, touch upon manufacturing in one way or another. So our first part, as I said, would be concentrating on what we call microscale transmission. And what we're going to look at is basically simple models for how pathogens propagate, for example, from a cough or a sneeze or things of that sort, and what controls basically the propagation of these types of materials. Now, in the simplest case, it's just simply some type of an explosive event here at the source. The particles are color-coded according to their sizes. And in general, what we're interested in is how far they go. In fact, they usually go, these are in meters, no more than roughly 2 meters, unless there's some external stimulus like a vent or some kind of a fan and so forth. It's hard to cough particles further than that. You really have to have some incredible set of circumstances. So generally speaking, it's hard to go to more than 2 meters, and we'll see why shortly. The drag effects really play a central role. And what we're seeing, at least in this simulation, which is what we'll discuss the nuts and bolts, is that the size of particles play a role in how far things go and also how long it takes for things to settle. Big particles, which are shown there in orange, they're roughly 200 microns in size. They go about 2 meters, which is what the CDC always tells us is the, horrible thing that is the distance part. What they don't like to talk about is the other part, which is the small particles shown there in blue. They remain airborne for quite some time because the drag from the surrounding fluid is so great that when you drop little tiny particles that are below a certain threshold size, it takes forever for these things to settle. So we have a dilemma that we have big pieces of spit that go far, but we have a lot of small stuff that remains airborne like a mist. And so, of course, if you think about, cologne or perfume, and you squirt that into the air, and you think to yourself, how long does that mist stay in airborne? It stays there quite some time because, of course, you can smell something that you spray mist, and then 5 minutes later, someone walks through the mist, they still have remnants of that smell. Well, guess what? I mean, unfortunately, that's what a lot of COVID-19 particles do. COVID-19 is pretty small, as we can see here. It's between 0.06 and 0.14 microns, depending upon the type of mutation and size of the objects. That's usually the upper and lower bounds of how big this stuff is. Now, that forces it then to sort of settle and take quite some time, but it also hitches a ride on pieces of spit. So if you have a piece of spit that is, 200 meters or 200 nanometers in size, microns in size, it basically will propagate quite some, distance because it's basically going to be attached to those particles. So generally speaking, if we're thinking about, what controls the dynamics of this, in the simplest case, we have F equals ma. This is almost like ballistically shooting out particles out of something and tracking where they go. And we have, of course, the acceleration of particles. Let's say the particles are numbered I equals 1 to the number of particles, the mass of the individual particles. The things that are acting on it are basically gravity and drag. Now, if we wanted to start to get fancy, and we could get very fancy, is we can start to consider also ventilation systems. And ventilation systems, of course, would depend upon what kind of object is around it that might be controlling the airstream. In fact, behind me there, that little thing back there, that cylindrical guy, that's a portable Levoit filter. And those things basically can, depending upon the settings, can dramatically change the airflow in a room relatively quickly. Now, That being the case, here's a simulation with all the parameters held the same, but there's a vent going upwards, and the vent kicks in right at around 1.5 meters. It's a pretty concentrated vent, and in fact, the airflow then picks up the particles and then drags them upwards. Now, there's good news and bad news. That means that, okay, well, if I was a 1.75 meters in this scenario, I'm safe because the particles aren't going to get to me. Hooray. The bad side is, well, if there's a vent that's pretty strong and it's not upward, there's a not hooray, because basically those particles are going to get transmitted closer and closer to me, depending upon how small they are. And in fact, if the small particles get entrained by an air stream, they can be transmitted quite some distance. So this was a problem that was brought to my attention by Lam Research. Of course, Lam is the biggest manufacturer of semiconducting devices on the planet. And Lam was concerned, where do the particles go, depending upon how our clean room settings are when we're doing manufacturing. And of course, that's a big deal, because in clean rooms, they have very specialized settings and airflows that are designed to take out contaminants, because contaminants, of course, ruin the integrated circuits or semiconductors. And so in this case, they cannot really alter the airflow easily, and the airflow is designed to actually take particles out. So unfortunately, in this case, if we have some kind of cough or emulsion, or emission here, generally speaking, if the vent was designed to take these particles away by carrying them across the room and then upwards, it puts a lot of people in harm's way. If there's another neighboring worker at a station that's roughly 6 feet away, they actually get a worse dose than if there was no ventilation. So this was a problem that was of concern. So the first question was, well, let's calculate what the drag forces are on the particles. In this case, the drag forces on the particles are given by what we call the classical drag law. We've seen this by now already when we started to work on the robot, and we worked on the robot problem. The robot problem primarily had a drag term for the stuff coming out of the dispenser. It is the same drag law that we have here, except that, of course, the surrounding air density is still the same. The drag coefficients, if we assume they're particles, those are still more or less the same. Of course, they're size dependent, as we'll see shortly. Then we have, of course, the flow of the fluid velocity. So the flow of the fluid velocity is where the vents come in. Depending upon what that is a control variable, this could have a big role in terms of the rest of the drag terms. And of course, then A is the bluff body or cross-sectional area of the objects. And in this case, the objects are those little spherical guys here that we see in the simulation. So this makes it a nonlinear ordinary differential equation, clearly. We have a problem that we have gravity, that's a piece of cake, that's just mg. But the drag terms clearly have a product of the velocity minus the velocity of the particle multiplied times a norm of the difference between the two. That's a nonlinear term that we can't really solve analytically easily. But of course, we've learned now quite a number of techniques to integrate this, and we'll look at that in a moment. So a lot of the impetus for this kind of modeling came from explosions. There was a large amount of work on explosions and hazardous materials that come out of explosions. For example, pathogens. Strangely enough, there was quite a bit of activity roughly between 2013 and 2015 on whether biological materials could withstand an explosive event and could actually get transmitted far enough to cause infections. There was quite a bit of fear of this, that if someone was infected and had an accident or there was an explosion, could that infected disease propagate then further outside of this sort of hellish nightmare of heat? The answer was, strangely enough, it turns out particles can, some types of pathogens can withstand a lot of heat. And so the idea was, is we would create artificial explosions because these are not an easy thing to obviously do in your backyard or to do the experiments. These were done, by the way, at Aberdeen Proving Grounds in Maryland with a colleague of mine, Jerry Caballo, who is a chemist and an infectious disease specialist. And Jerry's main issue was he would seed gelatin. This was a gelatin on a piece of a stand, and he likes to explode things. Jerry's that kind of guy. He exploded stuff and then would track basically with particle velocimetry where the particles were going. And we had very, very good correlation between simple models that used F equals ma for tracking of the particles, and then having these sort of simplistic drag type laws. They were remarkable in predicting the scatter and the distribution of particles from those kinds of an event. So let's look at the simplest type of model, and then we'll go systematically further and further. So Stokesian flow is the simplest model that we usually have. That's usually a model where the Reynolds number is nearly zero. So what that simply means is that inertia, which is the Reynolds number, is the ratio of inertia to friction forces. That ratio, when it's largely in favor of the friction forces, what it simply means is inertia doesn't play much of a role, and you can use the relatively simple drag law that we've seen as undergraduates, which is that there's a drag coefficient Ci, little ci. It's a function of the viscosity of the fluid. 6 pi r comes out from dimensional analysis, and the radius of the object or the particle that is in the fluid. Vi is the velocity of the particle itself. The nice thing about this differential equation is it's linear, so you can solve it analytically. It might not be easy to solve it analytically, but you can. So if you go through the process, and in the notes, I've gone through it, and I'll go through it again when we go through and do a deep dive on this, is that you can integrate this analytically, and you can find out that the velocity of the solution in each of the 3 directions is given by, for example, the velocity that it starts with, a ratio of some material constants that happen to appear in the differential equation, a ubiquitous parameter, the ratio of the drag term to drag force coefficient and the mass, multiplied times the time. So what you can see is there's an exponential decay of the velocity. It initially shoots out of the person, and then it dies down exponentially, and so it doesn't get any further. And that's a classical event that occurs with Stokesian types of flow. So I encourage you to solve this analytically, go through the derivation and analysis, and of course on the final I'll give you a lot of time, almost a week. So please keep that in mind, or put a little asterisk or a pin in this, that this is an important thing to understand how to integrate this analytically, and I show you that in the notes. So keep in mind that all of this is meticulously in the notes. Starting in chapter 11, we'll go through everything very, very carefully in the derivations, and we'll come back to that shortly. So the important thing is we can integrate this equation again, because not only do we want the velocity, we also want the position. If we integrate the position again, we get again something that is exponential. Obviously, the integral of an exponential is an exponential, but we also have a linear time term that occurs from the constants of integration, of integrating a velocity plus a constant. Clearly, we're going to have some kind of linear dependency with respect to time. The important takeaways here are, bottom line number 1, the ratio of the drag force to gravity is a certain set of parameters that occur. That's very important in any of these kinds of flow analyses, is to take the ratio of the drag force to gravity. That tells you a lot about how far things go and how long it takes for things to settle. So it's those 2 things that are playing off of each other. And what's most important here is to notice, what does that ratio tell us? It tells us, number 1, the viscosity of the fluid. The bigger the viscosity, the more dominant the drag force is. Well, that's a masters of the obvious question. If this stuff is thick syrup that is moving along and a particle gets trapped in it, the thick syrup is going to take it further than if it's a light, flitty fluid. So clearly, depending upon the viscosity, it will dominate a lot of how the friction forces are occurring. What's more interesting, however, is what's in the denominator. We notice that it's 1 over r squared. Now, what that means is that the drag forces are going to be super dominant as the particles get smaller, and it's not a linear effect. It's in fact a hyperbolic effect, meaning 1 over r squared, that if the particle is a centimeter in size and then a particle is a millimeter in size, and it's a tenth of a difference, it's 100 times greater of the drag force because it's 1 over r squared. So clearly there is a nonlinear effect that smaller particles take longer and longer time for them to settle. And that's in fact what we see in these simulations is the small particles there that are the ones in blue, they take forever to settle. And that's because exactly this ratio that we see there. Now, the decay of how long it takes for these events to occur is also given by C to M. C to M is that ratio that appears in all of these analytical derivations. And that ratio is, again, the friction term, or how friction forces are acting due to the surrounding material. So that's air in our case, although if it wasn't air, it would be something else. Of course, if it had no friction, it's a vacuum, more or less, or a very slippery type of gas. And of course, then gravity would dominate everything, and any object that would fall would go straight down according to the laws of ballistics, like we've learned as undergraduates in mechanics. In this case, however, it has also the 1 over r squared effect. So clearly what's happening is the velocities respond very quickly to external stimuli, but are controlled almost entirely by the surrounding fluid. So if you know the flow patterns, more or less the particles are going to follow the flow patterns after they've settled initially, then the flow patterns take it into account. So if the particles don't affect the fluid much, in other words, they're kind of just independent actors that are being launched into a fluid, pretty much the flow patterns of the fluid will tell you where the particles are going to go. Okay, now how long they take to settle and things like that, that would of course depend upon gravity. So bottom line number 3 is for small particles, drag dominates the settling process, and for larger particles, gravity dominates the process. That's the takeaway we have there. Now, if we start to get fancier and we say, you know what, Stokesian flow, that's wonderful, but maybe the Reynolds numbers are kind of big. How fast does a cough actually occur? Well, turns out coughs are pretty fast. Coughs and sneezes are roughly 30 meters per second. That's getting launched out there pretty fast. So if you've ever watched a time-lapse photography of a sneeze or a cough, those things are really getting shot out there. So it's possible that the Reynolds number could be, significant. And so since we have numerical tools and we don't care about analytics as being the end of the story, they're very helpful, of course, in determining trends. We might as well just simply clobber it with a simple ODE solver. The simple ODE solver is simply to do what? Is to integrate the velocity, as we've all been trained to do, by taking the forces on the other side, dividing by m, and then integrating basically v minus v at t plus delta t minus vi, and then basically rearranging the terms and then integrating it again. So this is 2 lines of MATLAB, 2 lines of, whatever, Python, Fortran, C, whatever you want. This is a piece of cake with an explicit Euler scheme. Now, one thing that is of concern is, number 1, what does the drag force really look like if we want to start to consider the Reynolds number and its changes? That's an important piece. Number 2, how many particles are out there? Are we talking like 10, 100, 1,000? It turns out that in most coughs and sneezes, it ranges from 300,000 particles emitted to 1,000 particles. So it varies wildly. What happens is that depending upon what, the saliva content, the behavior of a person, what type of medication they're taking, what time of year it is, I mean, whether they've had, a drink beforehand, all of those things play a role in how many particles come out of a person's mouth. So lots of what is going on in these kinds of simulations is to look at what if scenarios for every possible case. Someone has a cold, someone has a dry mouth, someone is 6'5", someone is 5'5". All of these different variations are things that you have to put into a kind of a simulator to be able to get some kind of information that a manufacturer might want in terms of trying to rearrange their manufacturing operation and so forth. Now, as I said, the Reynolds number, which is the ratio of inertia to friction, can be written in the following way for a spherical particle. The viscosity of air roughly is this in this case. So when you look at the Reynolds number, depending upon what range you have, Mr. Schlichting in the 1930s, 40s, and 50s, famous German aerodynamicist and fluid mechanician, went through quite a bit of analysis to actually categorize how the coefficient of drag depends upon the Reynolds number. And it turns out that he had basically a curve fit that he went through thousands and thousands of experiments to come up with an extremely accurate rendition of what the drag terms, what the drag coefficient looks like as a function of Reynolds number. And you've seen this already before in the robot problem, which is essentially you take 24 divided by Reynolds number. That's when the Reynolds number is teeny tiny. It turns out that will collapse back to, if you plug in this expression, it will collapse back to your nice Stokesian model you have here. So that one actually recovers exactly Stokesian flow if the Reynolds number is small. Okay, as it tends towards zero, it recovers exactly that differential equation. Between 1 and 400, you start to have a curve fit with curve fit parameters that Mr. Schlichting went painstakingly through. When the drag coefficient is about, over 400 to about 300,000, it's about 0.5, literally almost constant. Then it changes abruptly again with a nonlinear type of effect between 300,000 and 2 million. And then over 2 million, it's again roughly a constant. This curve is nuts. If you plotted out this curve, it goes up and down. It's not monotone. It has some discontinuities in it because of flow separation. And you start to think about, what does the drag coefficient really tell us? The drag coefficient, of course, is the effective force that is acting on an object. So if the fluid mechanics is complicated around that object, there's no reason to assume it's a smooth transition from one effect to another. The system might behave entirely different depending upon slight changes in the Reynolds number. And you see this in racket sports, most prominently table tennis. Ping pong balls have a extremely strange behavior depending upon how fast a shot is taken. They will separate and change from a sort of an arcing type of behavior into suddenly something that looks almost like a knuckleball or a floater. And that depends upon many different factors. One of them is the Reynolds number. And then another one, of course, is the spin. Depending upon the spin of a table tennis ball, you get the so-called Magnus effect, which is in fact makes things lift upwards depending upon the direction in which it flows. So for example, if you have a chop type behavior where you have backspin on a table tennis ball, you have a tendency to kind of float upwards, versus if you have a top spin, and that's of course what made many tennis players, of course, famous, but Rafael Nadal in particular, when he was in his prime in the early 2000s, he was absolutely shockingly different than many of the other tennis players in the sense that he had an extremely high topspin type of play that made him able to capitalize on the Magnus force of bringing in the ball, always landing in court, because of the combination of the velocity at which he hit and the topspin. The amount of RPM that was measured on tennis balls in the way he hit the ball was dramatically different than many of his opponents. I mean, everybody always uses topspin, but he used topspin in a way that was really a quantum level higher because of the technology that had started to occur in tennis rackets, in particular, the nanotexturing of the strings themselves bit into the tennis ball almost like little gears and allowed really almost a perfect contact that allowed the ball to basically be projected with much more spin. That's what occurs, of course, is the Magnus force that is this kind of effect. Now, the bottom line in these kinds of analyses, if you do the numerical analysis, which will be your final project, by the way, is to reproduce this kind of an effect, is what you see is that the large particles are settling quickly, small particles take forever, but they don't go far. So we're left with this kind of weird dilemma. Big particles go far, settle fast. You still have to clean them up because we don't want, obviously, spit and stuff in a manufacturing workplace, especially if they're contaminated. And at the same time, the small stuff sits there and remains for a very, very long time. So depending upon what the ambient velocities are, you can start to get crazy effects. For example, if the ambient velocity is 2 meters per second in the X direction, the particles gets transmitted over 8.7 meters. That's not a comforting thought. In other words, you have a wind velocity for some long distance, and it's only 2 meters per second. Those particles will get transmitted quite a bit of a distance. By the flip side, if the particles are small and you cough, but you're coughing into the wind, it doesn't take long for the wind to grab a hold of the small particles and transmit them backwards, roughly 8 meters backwards before they settle. This is for a 6-foot person coughing at roughly 6 feet above the ground. So these are things that were experimentally, verified. We went through a large number of tests with some colleagues in the department, particularly Professor Evan Variano in civil engineering, and then also Simo Makiharju in mechanical engineering. So these are important things that manufacturers want to know, but then really the money question is more of the following. Suppose I have a ventilation system. Again, I'm going to lean back there just like the one behind me. And we want to determine, okay, where should I put them so I can stop this thing from happening, because I need to sit and work in a place that is safe and secure, especially if I'm going to work there 8 hours in a clean room. I really want to know where to put these things so that, we can have HEPA filters that, scrub the air. Now, the problem, of course, there is as well, we hope everyone is wearing a mask, but of course, masks are, a placebo. I mean, unless you have an N95 mask and you're clean shaven, so I'm in kind of trouble, right? I mean, I wear an N95 mask, stuff is going to come out because of my beard. And so, of course, what I have to do is to shave. Well, I like my beard, so therefore I'm not going to shave, and I'm going to still wear the mask. And of course, we're going to have some problems. Many clean rooms are now mandating that, in fact, people have to shave and wear the mask, because even having razor stubble or something along those lines, if the mask is not perfectly fitting a person, it's going to squirt out particles. There's just no way to stop it. Now, how do we model a mask? A mask is a lot of charged little fibers, at least if it's an N95 mask, and it does a couple of things. Number one, it has pure resistive force of, pushing a particle through a forest of fibers. But if it was just that, it would just be a cloth mask. Really what happens is it goes one step further. The particles also, since they're small, they exhibit van der Waals type forces. And what happens is van der Waals type forces, basically the dielectric of the piece of material and the particles, they have sort of a static charge. They also charge the pieces of fiber in a way that they trap these things also electrically. Now that's where N95 masks become kind of hard to make. It isn't that somehow they have some magical property that they're just smaller fibers, and that's why it's harder to get a hold of these things. No, they're electrically charged. Little masks, those are charged with fibers that are called electrolets. The fibers are charged themselves. That means that if you wash that N95 mask, you're in trouble, because all of the electrical susceptibility of these things is gone. If you put it near some kind of an electrical appliance, you could actually, depending upon the electric fields, discharge your electric capability. So if you have an N95 mask and you value it, it would be a very good idea to put it always in a plastic pouch and away from electrically or magnetically sensitive devices, because they may have a tendency to deactivate your mask. So you have to be somewhat careful with how these things work. But the main features are van der Waals forces at small scales. They do have many layers of fibers, but those fibers happen to be also charged. However, nonetheless, studies have shown that even with the N95 masks, stuff is going to get out. People don't wear them properly. There maybe have holes in them. They reuse them. Whatever the case is, you really have to have some kind of filtration to be able to stop this stuff. So how do we model filtration or ventilation? Well, we have a couple of things. We have a model where we say, fine, we've got gravity. We had that before. We have drag, but drag now is going to include some control variable. That's going to be the flow of the velocity of the fluid. Then we also have the resistance to the mask, and the resistance of the mask is a term that is equal to the resistivity. So how much, resistance the mask, the fibers have per unit length, the velocity of the particles, and then the area of the surface area of the particles, because that's what's in contact with the fibers. If you put all that junk into the model, you also have a model for the ventilation system. A very simple one that's a classical one is to say that the velocity of the fluid surrounding the vent is strongest near the vent. Well, that's no surprise, but then has some radial exponential decay from the center of ventilation away from this object. So what that would mean is if I have a cylindrical kind of omniflow type device here, the further and further I get away from this thing, I'm going to have an exponential decay away from the device. So really far away, you don't even feel that the fluid is being affected by it. Nearby, you have a pretty strong effect. So let's play a game. Let's suppose we have 4 of these things and I can place them anywhere in a room. I'm going to control the flow rates of each of these things, and I'm going to control where I put them. And my question is I'd like to figure out the optimal configuration of where to put these guys in all the different locations. So I have a XYZ or X1, X2, X3 for each of these things. And then I have a flow rate of how fast the stuff is going to flow in or out. So it could be in or out. So if I go through this thing using our genetic algorithm, machine learning, that seems like it's tailor-made for this stuff. I have 16 parameters. The 16 parameters are all 3 locations times 4 vents. In this case, for this example, that's 12. And then 4 flow rates, that makes it 16. So let's suppose I have 16 parameters. I'm going to put these vents all over the place. And the question is, what's the best one to trap all the particles that might come out of this person's mouth if they cough? So we do painstaking analyses. We make someone cough. We calculate where the vents are. We compute where the particles go. And if this was a process that with an actual lab experiment, and I feel for my experimental colleagues, they actually had to do this. This is a very long and arduous thing to test. Clearly, cough, measure, this might take forever. But to accelerate the process is to do the simulations. And basically the simulations in this case, we develop a computer model. We have that. We just looked at it, F equals MA. We take the simulation results and we compare it to the desired results. In this case, the desired results are rather obvious. After a certain period of time, I don't want any particles anywhere. I want to have them be completely sequestered. So clearly, the cost function is a very simple one. It is 0 for desired, and however many are remaining out there, that's bad. So it's a very simple cost function. Count up the number of particles that are remaining after a certain amount of time. If there's anything out there, bad. So it's straight up particles that are airborne after a certain period of time. There's no reason to belabor this. I think we're all professionals now, where you've done the genetic algorithm 3 or 4 times by now. And probably if you had me in other classes, I've forced you to do that as well. They're very useful. We go through the same process as before. We generate a genetic string. In this case, it's going to be where the vents are and their flow rates. We're going to run a simulation, the one that does well, meaning particles mainly got trapped. Awesome. That's a good one. Stuff that makes the particles just sit and flounder all over the place. That's a bad one. And we're going to constantly keep re-updating these things over and over again until we get to the point where something is optimal. So here's the game I played in this simulation. I first said, fine, depending upon how greedy I am in sequestering the particles, if I say, look, after 1.75 seconds, I want everything out of there, the best this thing could do roughly was it got rid of roughly 65%, but 40, let's say around 35% in this first upper left-hand plot remained. So what that meant was the cost function adding up the particles is 0.36, meaning 36% of the particles were out there and I had no way to stop them. If I said, you know what, Tarek, you're being a little bit too demanding, let's wait for 2 seconds, not 1.5 seconds, 1.75 seconds, what happens? Well, in this case, the cost function went down to 0.12, meaning the best it could come up with is 12% of the particles still were out there, but there was still stuff out there. At 2.25 seconds, so I keep increasing it by 1/4 of a second, so not much, roughly then 2% of the particles remained out there. So 98% of them were sucked up by one of the vents. And then finally, if I went all the way to 2.5 seconds, within a very short period of time, it figured out the optimal design. And these, of course, are all the configurations, lambda 1 through 16, basically no particles remained. So simulation, for example, someone coughs, there's no ventilation, the stuff just flops onto the ground and gets carried further if the vents, if there happens to be some kind of wind current, eventually these things would basically take the particles pretty long clip. If you optimize it, the person coughs, depending upon where the vents are, and this is a bad optimization, what happens is the particles do get sequestered, but notice what happens right here. The particles actually get entrained and these two vents fight each other for domination of where those particles are. So it turns out, again, let's look at the simulation again, one vent being above, one vent being below, the small particles get transmitted a long distance. That's not good, because if I was standing in between the vent and the guy, I would have a problem. And number two, as we notice, the particles here are simply being split above and below, so they make kind of a band between the upper and lower parts. So it's not obvious where to put these vents. If you put two vents next to each other and they have flow patterns, if the flow patterns are weird, they will actually make the particles start to sit there and hover between those two locations. And so looking at the flow patterns of what the fluid is actually doing by basically computing the fluid mechanics of all of the different flows, we could start to see where the particles will go based upon what we sometimes call the streamlines. So basically, these are the pathways of where particles go between different possible vents. And this is just to show you an example of some of the splitting between the particles are going to this vent, some are going upwards. And so you really start to have some real action in here that if someone was unlucky enough to be between all of those vents, they would have probably a problem evading the disease. Now, those kinds of calculations are not easy. To compute the flow patterns of the fluid mechanics, you really need to solve the Navier-Stokes equations. And that, of course, is well beyond what we want to do in this class. But generally speaking, they're based upon taking the balance laws of mass, momentum, the constitutive laws. In this case, instead of the constitutive laws being Hookean, they're Stokesian type, where basically you have pressure type terms, gradients of, displacements and so forth, and gradients of velocities. If you solve all of these equations simultaneously, along with the first law of thermodynamics, collectively, that's called the Navier-Stokes equations. That's someone's entire life or dissertation would be basically, focused on that kind of a calculation. It's useful, but, a little bit beyond what we want to do in this class. But generally speaking, the approach would be very much like how you're doing the laser problem. You would discretize the entire domain of the room, for example. You would use finite differences or finite elements or finite volumes to basically compute all of the gradients and the derivatives of gradients and so forth. And then basically you would solve the thing using, a standard time stepping scheme. Again, very similar to how you're doing the laser type problem. Depending upon your optimization, what is really starting to become in vogue, especially in the fluid mechanics community, is to use artificial neural nets, not necessarily genetic algorithms. There are reasons for this. A large portion of the fluids codes that are out there mesh quite well with neural nets. And I don't want to get into the whole neural net business in this class, but there is some utility in possibly using those. And neural nets, as we, I think, have discussed, but I just briefly discuss it now, is more or less you have an input-output analysis where you have output that you want, you have input variables here that you control, and you basically take combinations of these parameters. You give each of the parameters a weight. You transmit that weight to a surrounding or a next layer of, or a node. What's in the dashed lines is the quote unquote artificial brain or neural net. You give each of these values a weight that says how much or how important, for example, is lambda 6 to the output. Then how important is lambda 6 transmitted from this node to the importance of the output. And if you do this properly, you can optimize what those weights are, what their activation functions are. So for example, when a piece of material or information comes to a node, how you process it is sometimes referred to as an activation function. There are on-off switches. They could be binary. They could be some linear processing. Those are part of the artificial neural net and part of the weighting system that occurs inside of here. So there are two pieces. There is the weight of how important that piece of material is coming in. And then number two is what you do with the processing when it gets in there. Now, depending upon how many layers you have here, so this obviously starts to become a little bit ad hoc. Deep neural nets basically consider, multiple layers. So how many layers? 6 layers, 10 layers. As you can see, every time you increase a layer, you increase the number of nodes, and you also increase the number of weights that are needed to weight this entire mess that you have here. Now, if you have a huge amount of data to calibrate and to train the neural net like you do in traffic, buying, for example, Facebook or Google or any of the other more or less large-scale advertisers, every time you click, you look at something, you buy something, Amazon, that is a piece of data that they can use to calibrate a neural net that is designed for you. So how they know your preferences is basically there's a neural net with my name on it somewhere out there that says, look, I like to buy the following kinds of things. I'm going to get the following kinds of advertisements. I mean, that's what has driven huge amounts of neural net activity is, of course, personalization of exactly what each individual is doing. Same thing with traffic patterns. What type of traffic, you're going to occur, what you see, the kind of data that you can use to train a neural net to be basically a traffic neural net is rather obvious. For manufacturing, not so sure. Honestly, it would require so much data to be able to calibrate and train these things that it is unclear whether that is really worth it, as opposed to simply using an optimization technique like genetic algorithms or gradient-based methods. So again, debatable. So I've talked for about an hour. I'd like to pause at this point before I go to part 2. And of course, on Thursday and the ensuing day, we'll go through many more of the details through pencil and paper and so forth. So packets, that are coming 22, 23, and so forth, I want to go through all of the details, but I want to give you sort of an overview. So before I hop right into part two and sort of the overview, are there any questions that you might have? All right. So oftentimes, once we're considering where these particles go, how far they've went, that's a victory in itself, or how to control the optimization of the ventilation systems. But at the end of the day, something is still going to have to be decontaminated. Now, the decontamination can be in many possible ways. Of course, to kill most pathogens, they're very sensitive to heat. If you heat up something, you can kill most pathogens. And of course, the most famous of these processes is pasteurization of milk, pasteurization of other types of materials. And that's, of course, heating more or less milk or any other kind of dairy product to roughly about 50 degrees C. What happens is it kills off most of the pathogens when you keep it there at a certain temperature, and then you can drop it back down again. And what happens is the pathogens are killed in an exponential way. This is the so-called microbial reduction classical equation, which simply tells us that N, which is the number of pathogens that are present in an object, is essentially going to exponentially decay depending upon the temperature. K is a rate constant, and depending upon how you control it, and if you can control it, you can kill quite an amount of stuff. Now, the problem is that's not going to work in a manufacturing workplace, because if you're a semiconductor manufacturer and you're thinking about a clean room and you're going to heat it all up so that you can kill all the stuff, number one, you'll kill your workers. And you say, oh, okay, fine, I'll evacuate the workers, get them out of there every day, and then I will heat up the stuff. Well, most of the stuff is plastic. You're going to destroy all the plastic, all of your gadgets, all of your lenses, all of your devices, your controls. That's not going to work either. So what has really taken hold in a lot of these is to use UVC light, which is basically ultraviolet C, which is roughly at the 254 nanometer scale, and to pulse different things in a manufacturing workplace. Of course, for food, people have used that for a long time. And essentially, what that boils down to is irradiating a surface and computing how much of that energy is absorbed. You can use a variety of different models. Beer-Lambert is certainly one of them, but it could be something even a little bit fancier, like I'm showing you here, with multiple pulses hitting a surface. And the question is how much of a dose is needed to kill off stuff on a surface. So even though you will not have an assignment on this, it's important to understand this in broader terms. So the basic idea there is that you compute, for example, how much energy income or comes into a certain object. In this case, it's a PPE, a personal protection, for your face, or personal protection equipment. And basically what I did is I computed the propagation using Maxwell's equations to compute how much of the energy gets reflected, how much gets absorbed onto this wavy surface. Now, how you would use such a tool, of course, is depending upon what you put in front of the gadget that you want to irradiate, you would have to, of course, alter what type of incoming energy you need to give the appropriate dose. If you give too much of a dose, you're going to melt or destroy whatever is being hit there. If you do too little, certain numbers of pathogens remain alive. So these kinds of analyses are basically designed to do very fast simulations of how energy gets propagated, how it interacts with the object, how it gets reflected. And that's based upon something called ray theory. Ray theory is a simplified version of Maxwell's equations. The primary interest there is tracking the amount of energy shown here in the arrows. That is the irradiation that you've already been working on in assignment number 6, which is that is the watts that comes out of the laser or whatever light emitting device. So if we're thinking about E cross H, that's the propagation of energy. It's the electric field crossed into the magnetic field. And then you have the pointing vector. So again, E cross H, propagation in the direction of, wave the wave propagation of the electromagnetic energy. That's what we're seeing here. Essentially, each one of those little arrows is E cross H, its magnitude, and as they reflect, hit the object and then reflect backwards, we compute how much gets absorbed. In this case, the little color-coded thing here is showing us how much of the energy got absorbed, and it's telling us the efficacy of exactly that pulse. And what we notice is in these little valleys where the reflection comes a bit askance, that not as much energy was absorbed as directly on the flat parts. So we have a little bit more reflection there on the curved surfaces. And of course, that's to be expected because in general, that's where you're not going to get full direct normal contact with the electromagnetic energy. So to look from the view from the top, what we see is in all of those little valleys, we see that there are different locations where the energy has come in at a different angle. And of course, in those cases, there the material is not as well irradiated as possible. So as a manufacturer or as a simulator, the question that you would ask is, well, okay, fine. This thing is not going to hit everything the way I thought it would hit. And what should I do? Well, to answer the question, either I can slow down the process, let's suppose it's a manufacturing process, and pulse a couple more times. But if I'm not happy with that and I have to do high throughput, so imagine the surface was a surface of strawberries. If it's a surface of strawberries and you were looking at exactly what actually would hit the surface, the question then would be, should I be moving the strawberries through here more quickly? Should I be doing them faster? Should I be stopping them? You know, many different possible questions would occur. And depending upon how we might want to do it, we might want to tell the person on the assembly line, you have to slow down everything because we have to irradiate them a little bit better. Or if we are thinking about food spoilage, if we irradiate them too hard, we'll actually destroy the food that we're actually trying to package up and sell. So clearly, depending upon how we want to do this, we might have completely different, configurations for these kinds of an event or kinds of events. So the point is that through these kinds of analyses, we can develop very fast tools that are able to, elucidate much of the information that we want, where we can use this to guide our experimental friends that are trying to design things in real time or do process control in real time. Now, there are some underpinnings of this. Many years ago, we used these same kind of techniques to basically pulse the human body with different wavelengths of light at a very low dosage in an attempt to determine what the reflections are based on cells. So this is sometimes called serology or optical serology. And the idea there is that you pulse cells that are in the bloodstream, and depending upon what the signature is of the cells, meaning what the reflections are, you could determine what kind of cells you're actually pulsing. Of course, that's a pretty good thing if you don't want to take blood, and if people don't want to be constantly getting peaked with a needle. This is a way to optically look straight into the bloodstream. These kinds of devices are sometimes called flow cytometers. They basically calculate the flow of a fluid through a small type of tube. Then the idea is that you use optical techniques, just like I showed you for the reflections of stuff. Now, depending upon what kind of cells are there, they'll give different signatures, statistically speaking. Now, at the time, we were interested primarily in thalassemia. So the idea was that we wanted to determine blood disorders and ascertain very quickly through an optical probe whether the person might have some liver problems. They might be suffering from acute alcoholism. They could be water dilution that often occurs when people are, have an imbalance in their sodium content. They become actually highly water content and bloated to a degree that could be life-threatening. They may have some type of iron deficiency. All of these different configurations will stop a normal, healthy figure 8 kind of cell and turn it into something that's pretty dangerous. And the pretty dangerous, of course, could be things like, for example, sickle cell anemia. And sickle cell anemia is prevalent in a wide swath of the equatorial population of this planet. And the interest there, or how it occurs, is what happens is hemoglobin that is inside the intercellular walls starts to polymerize and starts to produce little rods. These little rods cause the cells to start to become distorted. At first you think, well, what kind of a crazy disease is this? Why wasn't that sort of, died out, 10,000 years ago? It turns out sickle cell anemia starts to occur right when civilizations start. And the reason is that human beings started to aggregate near large bodies of water. And there were, of course, mosquitoes, and mosquitoes fed on people. And of course, people that contracted malaria died relatively quickly. Now, it turns out sickle cell anemia is a reaction to basically malaria. If you have sickle cell anemia, it turns out you're actually resistant or highly resistant to malaria. Sickle cells have a tendency to not allow the parasites associated with malaria to take hold because of the strange configurations of these cells. Now, that was a very useful genetic trait to have 10,000 years ago when you would die from malaria as a child or as a young adult. And most people didn't live to be past, let's say, 35 or 40 years old. So it was possibly a good thing to have sickle cell anemia. The problem is once people start to get older and they live past, 30, 35 years old, sickle cell anemia starts to lead to all kinds of other possible diseases, in particular anemia, because the red blood cell, which is our primary way that we get oxygen across our entire body, is no longer able to carry hemoglobin and oxygen. And so what happens is these cells don't bend easily. So the nice thing about red blood cells is they have this figure 8 shape. They can bend and skew, and they can go all over the place. They're very flexible, and they can get into the smallest of arteries and veins inside the human body. The problem is these things don't, and these things get clogged. And what happens is then oxygen can't get to the extremities, and then you're in big trouble, because depending upon how far the disease progresses, then you're looking either at serious lack of blood flow to the extremities, and in some case then amputation. So there really starts to become, the disease is not a nice one when it really starts to progress quite a bit further. So these kinds of things were determined optically when we started to look at these kinds of analyses of exactly how the material or the cells would respond. And so we were relatively well positioned to do things like decontamination analyses, because the codes are exactly the same. These are just different surfaces that are being hit with a number of rays, just like we had in the decontamination problems. And that allowed us to do all kinds of what if scenarios of shooting pulses of light through red blood cells. And these were actual experiments trying to ascertain how much of that energy was absorbed and how much of that energy passes through the red bloodstream. Just to give you an idea of, roughly in a cuvette of 1 centimeter blood, there were roughly 8,100 red blood cells available in each of these different experiments. So what we did is we took different concentrations of cells, we put them in a standard test chamber, we would shoot them with light, we would determine how much of the energy passed through, how much got absorbed, and then we basically did a correlation between the experiments shown here and the dotted line, the little dashes, and the actual what the code predicted. And the code was fitting right through this thing with relatively good accuracy. So we felt very comfortable with this kind of an approach. I'll stop here because I would like to pick up here when we talk about macroscale propagation, and needs a little bit more time, and I don't want to stop it in the middle. We'll talk a bit about contact tracing and epidemiology, and then we'll rewind and go through the details of exactly how these kinds of models occur and how we can use them, and that'll also warm you up for your last assignment. So Brian, do you have any kind of a timetable on when you think assignment 7 will get released?
So I'm planning on getting a draft to you by the end of this weekend, and if it passes, then I'll upload it by Monday or Tuesday.
Okay, sounds good. Of course, that'll be due at the end of the semester, at the end of reading, writing, and review. So you should have quite a bit of time. So don't panic about time-wise. You'll get plenty of time. I think that's May 7th, if I recall correctly. That's the end of reading, writing, and review. Are there any questions? Or if not, we'll call it a day and we'll pick up again on Thursday.
I had a question about
Sure.
the Stokesian
Yes.
equations that you had earlier.
Yes, just a moment. Get right back to it. Yes.
So in the very first equation, I was wondering how come there isn't a pressure term? Just from my understanding of the Navier-Stokes equations, which I'm presuming this is derived from, there is a pressure
Well,
term.
I mean, so in this form, it's just simply ballistic impact. It's basically the free body diagram of a particle. So that's the inertial part. There's the gravity, and then there's just the surrounding drag and its effect on the particle. So we're not actually computing the fluid mechanics here. We're computing the effect of the fluid on the particle itself. But if you were to look then at the fluid mechanics equation, so if we then said, well, wait a minute, what is the fluid doing? You're absolutely correct. We would have a pressure type term here, that's shown right there, that would occur in the constitutive law. But what we're doing is we're just looking at the effect of the fluid on the particles. We're assuming that the particles don't affect the fluid.
Okay, thank you.
Sure. Any other questions? All right, then. So have a good evening, and I'll see you all on Thursday.